Setting up a basic AI agent in n8n that can query a vector store is pretty easy, but getting it to consistently deliver relevant and high-quality answers requires some advanced techniques. And now, one of the easiest ways you can improve your RAG agent is to use re-rankers. Last week, n8n released this feature as part of version 1.98, where they now support Cohere's 3.5 re-ranker, and in this video, I'll be explaining what re-rankers are and how they can improve the accuracy of your AI agents. I'll show you how the new n8n Reranker feature works, along with some of the limitations that I have found, and I'll explain how you can get around these shortcomings and mix re-ranking with other advanced techniques like hybrid search to really improve the accuracy of your agents. Let's get into it. To explain re-ranking, let's first dive into what vector search is. Within a RAG agent, we typically perform a search across multiple documents. So when we process or ingest those documents into our vector store, what we do is we first chunk them or create segments of them, and those text segments are then transformed into numbers, as you can see here. And this is through the use of an embedding model. And these numbers essentially represent the meaning of the text. And all of those numbers are then stored in a vector database like Pinecone or Supabase. And you can see an example of this here. So we have a document, and you can see the color coding of this document, which represents the segments or the chunks. And when they are sent into an embedding model, we get back a vector point. And those points are plotted in three-dimensional space. Now, it's 2D here, but you get the idea. So if we look at the arrows, we can see that this paragraph is represented by this paragraph represented by this vector, etc. And then when a question is asked of an AI agent, we also convert that question into a vector. And we then query the vector database where all of the document vectors are stored, and we're trying to find the closest matches to the query vector. So back to our example, we can see all of our chunks plotted in three-dimensional space. And then we have a question, such as what rules govern the power unit of an F1 car? Once that's converted into a number and plotted, you can see that that dot represents this question. And then it's simply a case of figuring out which dots are closest to that dot that represents the question. And then the top chunks that are closest to the query are then sent into the LLM along with the question. So they're sent in as context. And then it uses that grounding to generate a response that's sent to the user. So there's a number of issues with this approach, and the main one being information loss. And the cause of this information loss is the compression of the meaning of this text. We're essentially compressing the meaning of that to be represented by a single point. So as a result of that, what you sometimes find is that the top results returned by a vector database aren't always the most relevant results. And the temptation to get around this problem is to simply increase the number of results you get back from the vector store. So instead of getting 3 results back, let's increase it to 6 or 9 or 12 or 15, and you keep going up and up and up. And while this might seem like a good approach, there are limits to the amount of information you can pass into an LLM. This is the LLM's context window, and there is a fixed length. And this technique of providing more and more information into prompts is what we call context stuffing. And even though some LLMs have large context windows where you can stuff large amounts of information into prompts, it doesn't always improve the LLM's ability to recall information. And in a lot of cases, it can actually degrade the performance of the agent. And this is seen in needle in the haystack tests that reveal lost in the middle problems. And what you'll find is information that's at the start and at the end of a prompt is prioritized over information that's in the middle. Models are improving in this regard, and I have created an entire video on cache augmented generation, where you essentially stuff all of the information of documents into a prompt. So if you are interested in that, check out the video linked in the card above. But generally speaking, one of the best solutions to this information loss problem is to maximize retrieval recall while also maximizing LLM recall. And this is essentially what re-ranking is. Re-ranking is often used with hybrid search. So if you're interested in implementing this in n8n, definitely check out my video on hybrid RAG. And later I'll be showing an implementation that uses metadata filtering, hybrid search, and re-ranking. So here we have all of our documents that are indexed in a vector store, and we have a query written by a user, which is sent into the vector store to find the closest matches. But as we previously discussed, because of this information loss, not everything returned from the vector store will be really relevant. So at this point, there are 25 results returned by the vector store are then sent into a re-ranker. And here we're asking for the top 3 most relevant results from this dataset. So with this approach, we're maximizing retrieval recall because we're able to increase the number of results coming from the vector store. And we're also maximizing LLM recall because we're not polluting an LLM's context with lots of different chunks that are somewhat irrelevant. So the key thing here is that from an accuracy perspective, re-rankers are much more accurate than embedding models. And one of the main reasons for this is that embedding models are known as bi-encoders. And what that means is the document chunk that's in the vector store and the query that's asked by the user are embedded in complete isolation, and they can be months apart as well. And that's how we find the distance between these 2 points in a vector store. So this approach is incredibly fast because you can do all the work up front to ingest the documents, so it works at very large scale, but as a result you do lose the accuracy because you can't look at both the query and the document at the same time. Whereas re-ranker models are what's known as cross-encoder models. So here the document chunk and the query are sent into the transformer model at the same time, and a similarity score is generated off the back of that. So as a result, they're much more accurate, but they're a lot slower. And the other thing is they operate at a much smaller scale. So you couldn't send in tens of thousands of chunks into a re-ranker model for every question asked. It's just not feasible. And this is why this technique is known as two-stage retrieval, because you could have tens of thousands of document chunks in a vector store, and stage 1 is a blunt instrument that gets the 25 most relevant results from the tens of thousands, and it's quite fast. And stage 2 then is highly refined, laser focused, and provides the top 3 in this example. Cohere's re-ranking models are the de facto standard in the industry, and they can be deployed on Azure, Google Cloud, Amazon Bedrock, but you can also just use Cohere's API platform itself to actually trigger the re-ranking feature. And they have various benchmarks which show how adding re-ranking to an AI agent can dramatically improve the accuracy of the results. And if you'd like to get access to all of our RAG workflows, including our ingestion pipelines, fine-tuning, metadata filtering, re-ranking, contextual retrieval, late chunking, then check out the link in the description to our community, the AI Automators. But now let's jump into the new Cohere re-ranker node that you have on n8n. Here I have a basic AI agent with a chat trigger. I have a Supabase vector store, and if you have version 1.98 or higher, you now have this re-rank results toggle. And when it's toggled on, you have a new leg from this node, which allows you to connect a re-ranker. Now currently there's only a single re-ranker that you can use, which is Cohere's, and that's what I've added here. And once you add this in, you simply just need to connect a credential, and all you need is the API key. So for this, go to cohere.com and create an account. And once you're logged in, go to API keys, and you can create and copy out the API key. And within your credential, just paste it in and click save, and you'll get your green connection tested successfully message. And once you save that, you can then choose your re-rank model. I'll choose the latest, which is 3.5. So I'll ask my question from earlier, what rules govern the power unit of an F1 car? So a lot happened there. Let's break it down. So we got our chat message, and if we click on logs on the vector store, you can see that that query was converted into an embedding, and then it went to the vector store to return the top 20 items, as you can see there. And these are then the input that was sent to the re-ranker node. So you can see we sent the query to Cohere, and we sent our 20 most relevant chunks, as you can see there. And what's fascinating about this, we're also sending the metadata associated with the chunk. Now, whether this is a good thing or a bad thing remains to be seen, because if you have a lot of unnecessary, irrelevant metadata, you could throw things off. But in a lot of cases, this could dramatically improve the ranking of the chunks within Cohere's model, because items within the metadata aren't taken into account as part of a vector search unless they're part of the embedding itself. So those 20 items have been sent to Cohere, and if we look at the output, we're getting the top 3 results back. And we're also getting the relevant score. So this one is 0.72348, this one is 0.72301. So you can see that it's actually ranked the chunks, and these are the top 3. So then in terms of maximizing the LLM recall, if we click on AI agent, and if we click on the LLM, you can see that we pass the system message, the user's message, and then we're only passing the top 3 chunks from Cohere. And as you can see, we're getting a pretty decent answer based off that context. And this leads me on to the main limitation of n8n's current implementation of this node, which is that if you click on vector store and when you enable re-rank results, there's no way to override the number of results that are returned by Cohere. It's hard-coded to 3 by default. So if you wanted to change this around completely, and let's say you wanted to maximize retrieval recall by getting the top 200 results from a RAG vector store, and then you wanted to fetch the top 10 that are re-ranked from those 200, there's currently no way to do that. I have created an issue on n8n's GitHub project to actually get this rectified so that we can have an additional field where we can override the number of results. And that way we can tweak and play around with what's the most effective number of results to get back from the re-ranker. The other thing I'd like to see is a flag where we can enable or disable the passing of metadata to the Cohere re-ranker. Because if you have a lot of metadata stuffed in there, it's going to throw off the re-ranking completely. And onto our more complex implementations of re-ranking with hybrid search and metadata filtering. This is all covered in our RAG masterclass and in our hybrid search video. But here I have an AI agent, and instead of having the vector store node as a tool, I'm simply triggering a sub workflow, which is this one down here. So if we ask the same question again, it's going to that sub workflow and it's getting back a response. And if we click into the executions, we can see what happened within this sub workflow. So it was triggered with the query rules governing an F1 power unit. We then prepped our metadata filters because within our RAG vector store, all of our chunks are tagged with different metadata values. Motorsport year, for example, motorsport category. So then this allows us to actually create subsets of vectors that we query so that we can get much more accurate results from those subsets. So here you can see motorsport category is F1. We then generate the embedding of the query, which is using OpenAI's text embedding small tree model. And we then trigger hybrid search in Supabase. And here as a body, we're passing the query text, which is used by the hybrid search system for full text search. We're passing the filters that were prepped in a previous node, and we're setting a match count. Now we could increase that to 20 or 100. And from there, the results that we get back go to our re-ranking model, where we actually trigger Cohere's re-ranker using a HTTP request node. And on the right-hand side, you can see that we get the various relevant scores for the chunks that we passed in. And finally, all of those are then returned to the AI agent so that it can simply formulate the response to the user. So if you'd like to see how this is done, check out the RAG masterclass and the hybrid search videos linked in the description below. If you'd like to improve the accuracy of your AI agents using advanced techniques like hybrid search, re-ranking, late chunking, contextual retrieval, metadata filtering, query expansion, and more, check out the link in the description to our community, the AI Automators, where you can join hundreds of fellow automators and builders all looking to leverage AI to automate their businesses. Thanks for watching, and I'll see you in the next one.